Welcome to the lecture on classifiers. So this is the point in the class at which we are going to change to our next major topic. So far we've talked about, in the main, regression. Problems where the target variable y is a real number or a real vector. And now we want to switch to a different problem, and this problem is called classification. In classification, the target variable v is categorical. It can only take a finite number of possible values, and we will call that set script v. Now these problems of classification are treated in a very similar way to regression, in that we will have a performance metric, have a loss function, do empirical risk minimization with regularizers. But then there are also specific attributes of classification problems which distinguish them from regression problems. In particular, we'll see that the type of loss functions we use is different, that there are particular types of error which can occur in a classification problem that cannot occur in a regression problem, and that there are ways of specifying the nature of the predictor for classification problems which are different from how we would do those in regression. We will also have a chance to talk about probabilistic regression in a later section of the class. Now the set script v, its elements are denoted v1 through v capital K, is called the label set. It's the set of possible values of v. The vi are called the classes or the labels or the categories. And when k is 2, this is called Boolean classification, in which case we usually think about script v as being true or false, or positive or negative. It's called multi-class classification when capital K is greater than 2, when we have more than 2 classes. Then our script v might be yes, maybe, no. It might be places or countries. It might be languages. It might be the set of English words in some dictionary. It might be the set of possible orderings of m horses in a race. So that's the m factorial set of permutations of the numbers 1 through m. Very often we just number our categories, and so instead of thinking them as v1 through v capital K, we think of them as just the numbers 1 through k. So when we're predicting a categorical raw output v, given a raw input u, that's called classification. We will talk about Boolean classification or multi-class classification. And the predictor is a map from script u, u is our set of possible independent variables, to script v, the set of target variables. We'll denote that by a capital G. Remember that in the regression section we talked about little g as being the predictor, and it was parameterized by theta. But also remember that little g was the map from x to y, where x was an embedding of u and y was an embedding of v. And so here we've named the map from u to v capital G. And so v hat is capital G of u is our prediction of v given u. And then G is called a classifier. And one way to think about the classification is to think about which values of u give a result of g of u is equal to 1, which values of u give a result of g of u is equal to 2, and so on. And if you think about that, then what we've done is we've classified the inputs u into k different categories, or k different classes. And those classes are mutually exclusive and collectively exhaustive. So here's an example. Here we have our set capital U as so capital U will be the square, the set of points U1, U2, where I think the absolute value of the components in this example is between -4 and 4. And our set V is equal to -1 or 1. We have two categories, one of which is -1 and the other of which is 1. And in this plot, you can see all of our data points. So here there's no split into training and test set. This is just the training set. And there are, I think, 100 points here. And so we've got 100 data points. And for each data point, we have a record consisting of a U, which will be a point in the square, and a V, which will either be a -1 or a 1. And so we have for I between 1 and n, where n is 100, ui is in script u the square, and little vi is either -1 or 1. And we've denoted the points here, we've shown them in the plot so that -1 here are points with points for which vi is -1 are shown as red points, and points for which vi equals 1 are shown as blue points. And so these are our 100 data points. Now what a classifier has to do is a classifier has to map every point in script u to either -1 or 1. So that if somebody comes along later and says, here's a new point in u, tell me what value for v you predict for it, give me v hat, well, that's what the classifier does. And we denoted that in this picture by shading the square. Some of it is shaded pink. Those points are points for which we predict an outcome which is -1. And some points are shaded blue where we predict an outcome of 1. And so if somebody comes along with some new point, let's make it some new point right here, then our prediction for that point would be that v hat is -1. If it's here, our prediction is that v hat is 1. And we're trying to learn the predictor capital G. We're trying to construct it. We're going to learn it from this data set. And this particular predictor, we haven't talked about how to construct it yet, but this particular predictor was learned from this particular data set. And you can see it does okay. In particular, if we look at how well is it doing on the training set, well, there are points such as these points where the true value of vi is 1 and the prediction, sorry, the true value of vi is -1 and the prediction is also -1. And there are points like these ones where the true value is 1 and the prediction is also 1. But then there are other points, like this red point right there. For that red point, the true value is -1 because it's a red point, but the predicted value is 1 because it's in the blue region. And so these are points for which our predictor is giving the wrong answer on the training data. And there are some points in the other which make a different type of error. There are blue points for which we predict the outcome should be red, and there are red points for which we predict the outcome should be blue. One way to think about this is it's a kind of regression, it's a kind of function fitting. Right? Instead of our function assigning a real number to every point, every possible value of u, our function is assigning a category to every possible value of u. The category either being -1 or 1, the category being red or blue. This is a good picture to have in your mind when you're thinking about what is a classification problem. You've got a bunch of data points, they have colors associated with them, and you want to shade in the plane so that the predictions corresponding to your shaded color match up with the true colors of the data points. And of course it's convenient to think like that, and in 2 dimensions of course the problem is kind of easy. We can simply shade in the plane to correspond to the colors of the points that we see, and there's no need for us to ever get it wrong. But if I'm working in d dimensions and d is large, well then I can't hope to do this by hand, and I have to come up with an algorithm that's going to do this for me. Let's talk about some applications of classification. Here's an example, medical diagnosis. U is a bunch of patient attributes, so the fields in a patient record are test results and age, gender, height, body mass, a whole bunch of other attributes of the person. And then the Boolean v, the target variable, encodes some disease status, has a disease or not, or maybe it's multi-class. Does the person have COVID-19, flu, or just a cold? If we're doing advertising, then U contains the attributes of a person, the demographic data about an individual. And it also contains information about an ad that's being shown to them. And then V encodes whether they will buy the item, whether they're going to click on the ad, etc. Fraud detection, so here U might contain the attributes of a transaction. Was it in person? Was it over the phone? Was it online? What kind of credit card it was? Was it international? And then V is an attempt to the categories that V can be are either that it's a fraudulent transaction or that it's a valid transaction. And so one might have a whole bunch of data where we have historical data of transactions, and they're labeled as to either being fraudulent transactions or valid transactions. And we would learn from that data a predictor that when somebody makes a new transaction, the attributes of that transaction can be fed into the predictor, and then the predictor would predict whether or not that transaction is fraudulent or valid. Image classification. Here U is an image. That would be an array of pixels. And V would be categories of possible objects within the image. So we might be looking to categorize natural objects, lions and tigers and bears, vegetation, trees, vehicles, buses, and we might build a classifier that you give it an image and it tells you what's in the image. And one can do simple things where one has an image which we know contains just one object, and the classifier has to return simply which object it is, in which case script v is just a list of possible objects. Or we might do more complicated things where the classifier has to return a list of all objects in the image. And that would be, and then in that case the script v would have to contain not just individual objects, but pairs of objects or lists of possible objects. Here's another one, spam filtering. This was one of the very first successes of the classification methodologies which we're discussing in this class, where U contains the attributes of a mail message, the from address, the to address, and also a description of the text in the email message, so which words are in the text in particular. And then V, the target variables, the categories would be either spam or ham. Ham, of course, meaning that it's a good email message. Back in the mid-1990s, when email was becoming very popular, a technique called Bayesian classification that we may see later in this class, we will certainly see related techniques, was one of the first successful methods of distinguishing spam from ham. Another example application of classification is sports forecasting. Here U contains the attributes of a game or a match, and team A versus team B, so which teams are playing, attributes of the teams themselves. And V encodes which game, which of the teams wins the game, or possibly a tie. Topic detection, so U is an article or a news item, and V encodes the topic, so politics, sports, or business, and so on. Another example is sentence parsing, so U is a sentence, and V encodes the grammatical parsing of the sentence. So that is a tree structure that encodes the relationships between the nouns, the verbs, the adjectives, the adverbs, and all of the other possible parts of speech. So when we're measuring the performance of a classifier, there's a very natural performance metric that we have that is probably the most commonly used, and that is the idea of the error rate. So if we have a data set with U1 through UN and V1 through Vn, so we have n records. For each one we have a UI and a VI pair, where UI lies in script U, and VI is the target variable, tells us which class UI belongs to. And then the predictions are given by V hat I, which is G of UI. And a prediction is correct if V hat is V, and it's wrong, or it's an error, if V hat is not V. The error rate, E, is the fraction of data points on which the predictor gave an incorrect prediction. So in other words, we look at all I from 1 up to n, we compare VI with V hat I, and if they're not the same, well, that's an error, and we count up the number of errors and divide by n. And this is the simplest possible performance metric for a classifier. And once we've computed it, we can use it to compare different classifiers, and in particular we would do this not only on the training set but on the test set. Now, when we're working on with Boolean classification, where the set of target variables, it has only two elements, we'll call them -1 and 1, then we refer to the class v is -1 as the negative class, and the class v is 1 as the positive class. And that allows us to use this very nice terminology about the possible outcomes. So we're going to be choosing v hat, that's what our predictor does for us, and we've got a true v, which is part of the training set. And if v hat is 1 and v is 1, well then that's a correct prediction, and we would call that kind of prediction a true positive. If v hat is -1 and v is -1, well that's also a correct prediction, and we'd call that a true negative. And then there are two different types of errors we can make. It could be that v is 1, but we predict that v hat is -1, and that's called a false negative or a type 2 error. Or it could be that v is -1 and v hat is 1, and that's called a false positive or a type 1 error. Now, once we've constructed a predictor, we can construct a statistic which describes the performance of the predictor. And that's this thing called a confusion matrix, C. It's a 2x2 matrix, and its entries are the number of true negatives, the number of false negatives, the number of false positives, and the number of true positives. And when we look at this, we should realize that the first column here corresponds to v equals -1, and the second one corresponds to v is equal to 1, and the first row corresponds to v hat is -1, and the second row corresponds to v hat is 1. So in the first row we pick v hat is -1. If we're in the first column also, then we've got a true negative. If we're in the second column, then we've got a false negative. We also refer to these entries individually as the number of true negatives, the number of false positives, the number of false negatives, and the number of true positives. CTN, CFN, CFP, and CTP. And these are numbers, not rates, so if we add up those four numbers, they add up to n, which is the total number of data points we have, the total number of examples. We also have the number of negative examples, which we'll denote by n with a little n as a subscript. It's the number of true negatives plus the number of false positives. And the number of positive examples, which is the number of false negatives plus the number of true positives. And these are sums over the columns. So this sum right here, CTN plus CFP, that's equal to n, the number of negative examples. And this sum right here is equal to np, the number of positive examples. When we look at this matrix, of course, how do we get this matrix? Well, we have a predictor G, and we can evaluate it on the training set, and that will give us a matrix C. And we can evaluate it on the test set, and that will give us another matrix C. And these two matrices, these two confusion matrices, are measurements of performance. And when we look at them, well, what we'd like to see is large numbers on the diagonal, because the diagonals are measurements of the number of times in which we've made correct predictions, and small numbers in the off-diagonal, because the off-diagonal entries are incorrect predictions, and that's what they're counting. And they're counting separately the two different types of incorrect predictions, and the diagonals are counting separately the two different types of correct predictions. Now, there are some very standard terminology that surrounds the confusion matrix that's worth going over. In particular, the false positive rate is simply CFP divided by n, and the false negative rate is CFN divided by n, and the error rate is the sum of those two, CFP plus CFN divided by n. There's also a whole bunch of other terminology that people like to use, often in very specific fields. So people talk about the true positive rate, or the sensitivity, or the recall. That's CTP over NP. It's the fraction of true positives which we guess correctly. The false alarm rate is CFP on NN. The fraction of true negatives we incorrectly guess as positive. There's the specificity, or the true negative rate, which is CTN on NN. The fraction of true negatives that we correctly guess. And there's the precision, which is CTP on CTP plus CFP, which is the fraction of our positive guesses that really are positive. And these are, well, they're used in different fields. Quite a lot of them are used in medicine. Some of them are used in specific branches of statistics. We will, I think, never use things like sensitivity or specificity in this class. In machine learning, almost always people just look at the confusion matrix and the counts, which are readily interpretable and readily converted to one of these other meshes if you're working in that appropriate field. Now, one of the things about looking at the confusion matrix is that it highlights for us that we have really two metrics for a Boolean classifier. We'd like to keep both the false positive rate small and the false negative rate small. And the sum of those two numbers is the error rate. And keeping the error rate small is fine, but sometimes it's not what you want out of a classifier. So, for example, if you have a manufacturing line, you have a camera that's looking at the objects that are coming off the manufacturing line and is trying to determine whether or not they are correctly manufactured or incorrectly manufactured. If you've got very few errors in your manufacturing process, then a huge percentage of those manufactured objects will actually be correctly manufactured, and only a very, very small percentage will be incorrectly manufactured. Classification is often difficult for such manufacturing problems, and very often the predictor that minimizes the error rate is simply to predict that all of the objects coming off your production line are actually correctly manufactured. However, that's completely useless, of course, because it's giving you no information. What you're much more interested in such a situation is to be able to detect those bad objects, those incorrectly produced objects. And so one would have a classifier there that is willing to incorrectly classify a few good objects as bad, as long as it caught most of the bad objects. And so there one is quite happy to accept a few false positives, positive here corresponding to bad objects, in exchange for a very small number of false negatives, for where the false negatives there would be incorrectly assuming that a bad object is good. This is a very common situation, that the thing you're trying to detect is rare, and so choosing a classifier that minimizes the error gives us an uninformative classifier, and it's much better to try to choose a classifier that focuses on either false positives or false negatives. Now, we still need to be able to compare classifiers, and it's very often convenient to have a single metric, a number. And the way we do that is we combine them with a weight. So, and that's called the Neyman Pearson metric, ENP. It's kappa times the false negative rate plus the false positive rate. And so here kappa is some positive number, and it sets how much we care about false negatives compared to false positives. So kappa is very large, then our Neyman Pearson metric is affected very much by false negatives and not so much by false positives. If kappa is very small, then our Neyman Pearson metric is large when we've got a large number of false positives and not so much when we've got a large number of false negatives. And if kappa is 1, well then the Neyman Pearson metric is just the sum of the false negative rate and the false positive rate, which is the error rate. Let's look at this more conveniently as a trade-off graph. If you pick any classifier, you designed it using whatever your favorite method of designing classifiers is, and we haven't told you how to do that yet. And then you say, well, okay, I've got a classifier, and I can compute its false negative and false positive rate on the test set. And those are going to give me two numbers. And I can plot those two numbers on this plot right here. So on the horizontal axis here, I've got the false negative rate, and the vertical axis, I've got the false positive rate. And so you give me any classifier, it has some particular point. There's one, here's another. And so different classifiers correspond to different points on this plot. Now, one thing that's worth observing on this plot is that there are some classifiers that you would just never use. One is G3. And the reason you would never use G3 is that if you compare it with G2, well, G2 does better in terms of the false positive rate and the false negative rate. And so G2 wins on both counts, and if you're interested, even if you're more concerned about one of those measures than the other one, you'd still use G2 over G3. If on the other hand we compare with G1, well, if I compare G1 with G3, well, G1 does better in the false negative rate, but worse in the false positive rate. And so I might well use G3 instead of G1. But if I've got G2, I would use G2 over G3. Now, if I compare G1 and G2, well, that's not so easy, because G1 has a smaller false negative rate, but a larger false positive rate than G2. And those two classifiers are incomparable. Choosing between them is up to you, the designer of the system. You may be more interested in keeping the false negative rate small. If you're more interested in keeping the false negative rate small, then you should choose G1. If you're more interested in keeping the false positive rate small, then you should choose G2. If you have G2 available, then you should never choose G3. So when you look at a classifier on this plot, the important classifiers are those for which there is nothing better in both false positive and false negative. So if I look at a particular classifier and say, let's look at G2, and then if I draw here the region of the plane consisting of values for the false positive and the false negative rate which are better than those achieved by G2, if there's no classifier in that region, then it's a good classifier. Conversely, if I look at G3 and I look at the region consisting of better performance, well, there are classifiers in that region. So G3 is a bad classifier. Now, the good classifiers have a name. They're called Pareto optimal. they're good because no other classifier is better in both false positive and false negative rates. The set of all of these Pareto optimal classifiers, so the Pareto optimal classifiers are these red points. So the set of all Pareto optimal points is called the operating characteristic, or the ROC. ROC stands for receiver operating characteristic. This is a term that goes back to the design of radar systems in World War II, and almost nobody calls it the receiver operating characteristic anymore. Almost always it's just referred to as the ROC. And so what we commonly do is we develop many different classifiers, and we plot them on this plot. We rule out the ones which are bad, which are not Pareto, and then out of the ones that are Pareto, we get to make our choice. Now, when we've got the Neyman Pearson measure, that's kappa times the false negative rate plus the false positive rate, well, what that's doing is it's measuring performance in a particular direction in this plane. And so when I think about this, I'll call, I've got the false negative rate and the false positive rate, and I can, if I've got a particular kappa, I can draw a vector. There's a vector, and that vector is in the direction kappa 1. And so I can think about my Neyman Pearson metric as kappa 1 transpose CFN on N, CFP on N. Now, because we're using the vector kappa 1 multiplied by the vector of coordinates in this plane, what that measures is it measures the distance from the origin in the direction kappa 1. And so if we look at the set of all points for which kappa 1 transpose multiplied by the coordinates of that point is equal to, say, 1, that would be a line here. And then if we look at the set of all points for which that linear combination kappa 1 transpose multiplied by the coordinates is equal to 2, there would be a different line, and so on. And so by minimizing kappa times the false negative rate plus the false positive rate, we are trying to pick the point that is on the line of these lines which is closest to the origin. In this particular case, the point is G2 for this particular value of kappa shown here. And these lines have a slope of minus k, minus kappa, and so by varying kappa between 0 and infinity, we have slopes. When kappa is 0, we have a vector pointing in this direction, and when kappa is very large, we have a vector pointing in this direction. So we can pick kappa according to our preference. If we make kappa very large, then we're going to try and minimize. We're going to have a slope lines that look like this, and we're going to be concerned about performance, where the best thing one can do in order to make the performance measure small is to choose a predictor that has a low false negative rate. if instead we use a kappa which is very small, well then kappa 1 looks a vector like this, and we're going to have corresponding lines in this direction. And the best thing we can do to make that performance metric small is to pick a predictor for which the false positive rate is small. Here's an example. Here we have the same data set that we showed before. We have blue points and red points. The red points are -1, and the blue points have target variable 1. We can see there are some false negatives. The false negatives are blue points for which the classifier would predict red. So, where is a false negative? There's one false negative right in there. Underneath there was a blue dot, which I will now make visible. There it is. So this blue dot there is in the red region. It's in the region which our classifier would predict red. That's a false negative. And then there are many false positives. Right? All of these red dots are points which we would predict as blue. We'd give a positive prediction, but it's a false positive. If you count the number of red dots, the false in the blue region, that for classifier number 1, that turns out to be 16. And we've already seen that there's one blue dot in the red region. And so this here is our false negative. This here is our 16 false positives. These are correct predictions of -1. So these are red dots in the red region, and there are 24 such red dots. And these are blue dots in the blue region, and there are 59 such blue dots. Now, if we, on this particular test, on this particular example, there are 100 points, and so the false negative rate is 0.01, and the false positive rate is 0.16. And we can plot those. False negative rate is 0.01, false positive rate is 0.16. Well, there's 0.01, there's 0.16. That's predictor 1 right there. We can look at predictor 2. This is a different predictor. You can see it's got different regions. And this predictor is encompassed more. So when you look at this set of data points, you can see that it's largely let me erase that. It largely consists of blue points going across the middle here and red points going this way. And so our predictor here is focused on getting the blue points covered by blue region, and unfortunately it's going to have some red points covered as well. And that's why it's got a large number of false positives, because the red points are being classified as blue. Here we've said, well, we don't want that anymore. We would like to balance the red and blue errors, and so we've got a predictor that is classifying more of the red points as actually red. More of the region in which the red points are has a corresponding prediction of red. As a result, we can look here and we can see, well, now there are 8 false negatives. There's one. But there's only 8 false positives. Here's one. And that gives us corresponding false positive and false negative rates of 0.08, which is right there. Here's a plot number 3 is a classifier at the other extreme. Here we've tried to focus on getting the red points correct, and in exchange we're getting some of the blue points wrong. What does that mean in terms of false positives and false negatives? It means that we've got very few false positives and a large number of false negatives. Our false positives are red points that are classified as blue, and there are 2 of them. Here is one of them. And we've got a large number of blue points that are classified as red. There's one of them. Our resulting counts there are 23 false negatives and 2 false positives, and that gives us this classifier right there. So there are 3 classifiers, and which one you pick out of those 3, that's up to you. There is no way of choosing between these 3 classifiers. Number 2 beats number 3 in false negative rate, but does worse in false positive rate. Number 1 beats number 2 in the same way. Neither one of them, we would say neither one of them dominates the other. And so this is a design question. It depends on the particular problem that you're looking at, whether you're interested in a classifier that has smallest overall error rate. Let's look at what the overall error rates are. So this one has an error rate of 17, this one has an error rate of 16, and this one has an error rate of 25. And those are, of course, error counts. Error rates are 0.17, 0.16, and 0.25. So the one with the smallest error rate is number 2. The one with the smallest number of false negatives is number 1, and the one with the smallest number of false positives is number 3. Now when you look at multi-class classification, well, there are no longer just 4 possible values for v hat and v. There are k squared possible values, because there are k classes, v1 through v capital K, and each of v hat and v can be in any one of those classes. So there are k squared possible outcome pairs. When we say v hat is vi and v is vj, it means the true value is vj and we're predicting vi. So the only ones that are correct are when vi is vj. And it's incorrect when vi is not vj. In other words, if v hat is v, that's correct, and if v hat is not v, that's incorrect. So there are k different ways in which we can make a correct prediction. If we predict v1 and the truth is v1, that's correct. If we predict v2 and the truth is v2, that's also correct. But there's also a bunch of different errors. If we predict v1 but the truth is v2, well then that's an error. But there's a different error where the truth is v2 and we predicted v3. So there are k times k minus 1 types of errors, one for each possible pair where I is not equal to j. So we have a k by k confusion matrix, and the ijth entry of the confusion matrix C is the number of data records where we predicted v hat was vi but actually the true v was vj. You should be aware that sometimes people transpose this, so they swap I and j, and of course that's just a convention. Of course, the entries in C add up to n, the number of data points. The column sums give the number of records in each class. CII is the number of times we predicted VI correctly. If I is not j, then Cij is the number of times we mistook Vj for Vi. Now these quantities, Cij, where I is not equal to j, if we normalize them by the number of records n, that's called the error rate for those particular pair of classes. Eij is the fraction of the data points on which we mistake Vj for Vi. And the overall error rate is the sum of all the different error rates. So here's an example. Here we've shown data points which have target value 1 as red, 2 as green, and 3 as blue. And we've got a classifier that classifies points in the plane as either red, green, or blue. And you can see that it's doing okay. The green region mostly contains green points, the blue region mostly contains blue points, and the red region mostly contains red points. There are a few cases where we have green points, but they would be predicted as red. Here's 1, 2, 3, 4, 5. So those are green points that we would predict as red. And there's a blue point that we would predict as red as well. That's this one right here. And so there's one of that type of error as well. What other types of error are there? There's a red point that we are predicting as green. There. That's this error. And there's a green point that we're predicting as blue. That's this point right there. And that's this error. All the other points are correctly classified. We've got 39 reds that we're classifying as red, 34 greens that we're classifying as green, and 17 blues that we're classifying as blue. Now to take the error rates, well, there are 100 points, so I simply take all the non-diagonal, all the off-diagonal entries of the confusion matrix, divide them by 100, and that gives me the error rate matrix there. And if I sum up all of these different errors, I'll find there's a 10% error rate. Now, just as in the Boolean case, when we want to pick a classifier, it's very often convenient to have one number that measures, that is our performance metric. And the way we would do that is we would use a weighted sum of the different types of errors. Now you could attach a weight to all of the different categories of errors. So in our 3-class example, there are 6 possible types of errors. And so you could have 6 different kappa values and use those 6 different kappa values to weight the different errors. And that would be a perfectly fine performance measure. In fact, we don't do that. What instead we tend to do is we tend to use a kappa value which is only defined per column, per true class. And so we'll have one weight which is associated with these 2 errors, one weight associated with these 2 errors, and one weight associated with those 2 errors in the last column. And so associated with each column, there's the error rate, which is denoted by E sub j. It's the number of times we mistook Vj for some other class. And we could divide by n and get the error rate as well as the error count. And then we take a weighted sum of these three error rates, and that's the Neyman Pearson error. So kappa j is then how much we care about mistaking Vj for something else. And if kappa j is 1 for all of the different i's, then the Neyman Pearson error is the error rate. We're just summing up all the different errors. So to summarize, in this section we've talked about how you measure performance of classifiers, both for Boolean classifiers and for multi-class classifiers. We haven't yet talked about how you find classifiers, and that's coming in the next section.